Okay guys, let's look at section 10.3, and in this section we're going to actually discuss three more types of convergence tests. The first of those, and probably honestly the least beneficial of the ones in this section, is the integral test. One of the things that makes the integral test a bit annoying to use is you've got to be able to ensure that it can be used in the first part of it, and in order to ensure that it can be used, the function that would represent a term within the general term of the series, the function f of x that represents it has to be positive, decreasing, and continuous. Has to satisfy all three of those criteria. Then if it does, the general term of our series that I'm calling f of n here will converge or diverge if the series from some number m to infinity of f of x dx converges or diverges, where m is any finite number. It can be the same base as whatever n is. It doesn't have to be, though. M is any finite number. Now, as long as I can show that the integral diverges, well, then the corresponding series would diverge. If I can show that the integral converges, then the corresponding series would converge. Let's show how that works within a problem. Anytime I'm asking for integral test, I'll always abbreviate it with capital IT. Use the integral test to determine if the series from 1 to infinity of n e to the negative n squared converges or diverges. Well, the corresponding function here, and remember, you cannot put the n's down here because n is only for integer values or for counting values of n. So this is only valid for n equals 1, 2, 3, 4, 5, and so forth. The function that refers to it is going to involve all values, so we usually switch it to terms of x, showing that it exists for fractional values, irrationals, rationals, all numbers. So the function corresponding to this would be x e to the negative x squared. Now, in this function, I can quickly and easily see it's continuous and positive. The way I know it's continuous is because it's the product of two continuous functions. Y equals x is continuous, and all exponential functions are continuous. The product of two continuous functions is continuous. I can also easily see it's positive for any x value that's greater than 0, because x is going to be positive, and all exponential functions are always positive. So I can say, okay, continuous and positive, easy to show. The one that's usually difficult to show is this second one, the decreasing. I did that right here. So for this function, how do I show it's decreasing everywhere I'm interested in doing the integral? Well, I need to show that the first derivative is equal to some negative value. So I need to show the first derivative is negative. I go ahead and take the first derivative here, use the product rule. Derivative of x is 1 times e to the negative x squared plus x, now times the derivative of the second. Derivative of that exponential function is that exponential function times the derivative of its exponent. Now I can factor out an e to the negative x squared, and when I do, I'm left with 1 minus 2x squared. I set that equal to 0 to find my critical points, and I can say, well, the first factor can't equal 0 anyway because exponential functions are always positive. So the only critical point you're going to get is by setting the second factor equal to 0. That gives you 1 is equal to 2x squared. 1/2 is x squared. Square root of both sides, you'd get plus or minus 1 over the root of 2. I went ahead and rationalized, though I normally don't, but it's no big deal here, plus or minus the square root of 2 over 2. Now, the only value that we need is the positive. So I went ahead and just checked what about the critical point, the square root of 2 over 2, and I want to determine what is the sign of the derivative from the square root of 2 over 2 towards infinity. So I use my first derivative sign test. This is the interval I'm interested in, and I know it will never ever change sign again after the root of 2 over 2 because that's my last critical point. It can only change sign at a critical point. So I go from square root of 2 over 2 to infinity. I'm choosing x equal 2 to represent that interval. I plug that into my first derivative, factored first derivative preferably, and please notice that exponential function always positive no matter what you plug into it. That second factor, 1 minus 2 times 2 squared, would become a 1 minus a to be a negative 7. The number doesn't matter. It only matters the sign. I know that my first derivative would be negative product in this region. A positive times a negative is a negative. Anywhere your first derivative is negative, we know our function is decreasing. So that's why I said, therefore, this function is continuous, positive, and decreasing. Now the square root of 2 over 2 is like 0.707. So clearly if it's decreasing from 0.707 to infinity, I can say it's decreasing from the next integer value up from 1 to infinity. Now it would be incorrect to say it's decreasing from 0 to infinity, but I didn't need to say that anyway. So 1 to infinity, absolutely fine. Here's the integral test. So now keep in mind, all of this isn't technically part of the integral test, but all of this had to be thought of to begin with before I could even initiate the integral test. Now, here's the integral test. Integrate the function from 1 to infinity, x e to the negative x squared dx. I went ahead and made it a proper integral since it had a infinity as a limit of integration. I said limit as b approaches infinity of the integral from 1 to b. And then I looked on the inside and said, well, this is going to work really nice with substitution. I can let u is equal to negative x squared. Derivative of that would be negative 2x dx. I know I don't have a factor of negative 2 on the inside, so I would multiply the inside by negative 2 as I divide the outside by negative 2. That's where the negative 1/2 came from on the outside. And then the part on the inside just becomes e to the u du. Now, I didn't want to change my limits of integration, so you'll notice I left my limits in terms of x. This is from x equals 1 to x equals b. I come down in my next step. This integral is going to equal the limit as b approaches infinity of negative 1/2 e to the u. The integral of e to the u is e to the u. Evaluated from x equals 1 to x equals b. In the next step, I just plugged back in my substituted value of u is equal to negative x squared. And then notice, whenever we're evaluating this, you can say, well, your upper limit is going to be the limit as b approaches infinity of negative 1 over 2 e to the negative b squared power. From that, you need to subtract the lower limit, but minus a negative 1/2 became plus 1/2, and then I had e raised to the negative 1 power. Now, this first one just becomes 0, and that needs to be absolutely clear to you when I say that that first term becomes 0. The reason is because if you plug in an infinity for b, doesn't matter that it's being squared, please notice that negative is not being squared, only b is squared. So you'd say, well, that's just going to be negative infinity. Well, e to the negative infinity means that that exponential function is in the denominator. You're going to have negative 1 divided by 2 times infinity. That's going off towards 0. Anytime any finite number is divided by any infinite number, your answer is 0. So the first whole term becomes 0. The second, similarly, even though it's not an infinity, it's a negative exponent. That e belongs in the denominator, and you'd have 1 over 2e. Now the answer to this problem, 1 over 2e, shows me that this integral converges because it has a finite answer, 1 over 2e. The integral converges to 1 over 2e. And then I can say, well, since the integral of this function converges, the corresponding series n e to the negative n squared also converges. Now, a common mistake students will want to make is they'll try to read too much into the power of the integral test, and they'll want to say that the series also converges to 1 over 2e. That's wrong. We don't know what it converges to. We just know that it does converge. So since the integral converges, the corresponding series also converges, but it does not converge to the 1 over 2e. Remember, this is only true for counting numbers of n, where this had to include all values of x. So they're not going to have the exact same convergence answer as far as what they converge to, but they both will converge at the same time. Now, the integral test is helpful in forming our next type of test that we're going to be talking about with the comparison test. Before we do the comparison test, let me remind you of what we talked about in section 10.2 with the p-series. P-series is going to be the most basic format of these series. It's whenever we have 1 over n to a power. And those will always converge if and only if the value of p, the power there, is greater than 1. So that denominator has to get large fast for that fraction to get small enough to not diverge. Anytime that denominator doesn't get large enough fast enough, then you're going to incur too much area under the curve and it's going to diverge off to infinity. So a lot of times students get confused because they're like, well, wait a minute, it diverges if p is small and converges if p is large. That should make sense to you, because if p is large, that means your denominator is getting large fast, which means your fraction gets small fast. Thus, it has a convergent answer. If p is some small number, then that means your denominator is not getting large enough fast enough in order to make the fraction small enough to converge to some small answer. In that case, it diverges. Now, I want to verify this p-series analysis with the integral test. Well, if I plug in a 0.9 into the corresponding integral here, instead of 1 over n to the 0.9, I'd have 1 over x to the 0.9. I'm evaluating that from 1 to infinity. So this becomes the limit as b approaches infinity. If x is 0.9, we know that if that x to the 0.9 is in the denominator, we know it's really the same thing as x to the negative 0.9. And then whenever you integrate, you add 1 to that exponent. X to the negative 0.9 becomes x to the positive 0.1. If you divide by 1/10, then that's the same thing as multiplying by 10. So we end up with the limit as b approaches infinity of 10x to the 0.1 power evaluated from 1 to b. Now instantly you need to see, well, this goes off to infinity. Why? Well, because if you let b go to infinity, you're going to have 10 times infinity to the 0.1 power. Infinity to any positive exponent is infinity. 10 times infinity, clearly still infinity. The lower limit's irrelevant since it's just a finite value. Infinity minus any finite value, still infinity. Now, when I look at the p-series test with 1, it should also diverge here according to the formula. The corresponding integral will also verify that. If p is 1, then you're just going to have 1 over x to the first. And we already know the integral of that is going to be the natural log of x. So I can say, well, this is the same thing as the limit as b approaches infinity of 1 to b of 1 over x dx. And then I can say, well, that's the limit as b approaches infinity of the natural log of x evaluated from 1 to b. You didn't need an absolute value here since all of your limits are positive. Now, if I plug in that top limit of b as b approaches infinity, and you say, well, the natural log of infinity is infinity. So again, this integral would diverge, which means the corresponding series 1 over n to the first also diverges. Now, anytime that it's the p-series with p equals 1, this is our smallest possible divergent series. So the natural log of infinity is the smallest infinity in existence. Even if you had something like in the top problem, even if that exponent was 0.00000000001 and I had infinity raised to that power, it's still a larger infinity than this infinity. The natural log is the smallest possible infinity possible, and you'll see here we call it the harmonic series. Now, the next scenario I want to look at, which should agree with this, we know that in the p-series, anytime p is greater than 1, that's going to be evidence that our series is convergent, that the denominator is getting large enough, fast enough to make the fraction small to converge to some finite value. In order to show that, I've put a number just slightly larger than 1 down here. So this would be a p-series with p equals 1.1. 1 over x to the 1.1, it should become obvious right now why this is going to converge. Because whenever we rewrite this as a x to the negative exponent, you can see, hey, that negative exponent is more negative than a negative 1. So whenever you do your power rule, it's going to stay a negative exponent. That term goes to the denominator, which means you're going to be dividing by infinity instead of having an infinity in the numerator. Automatically it's going to converge. So in this case, x to the negative 1.1 integrated to x to the negative 0.1, which gave me x to the 0.1 in the denominator. And then I was thinking, well, it's x to the negative 0.1 divided by a negative 0.1. Same thing as multiplying by negative 10. That's where the negative 10 came from in the numerator over x to the 0.1. If you evaluate this at infinity, the infinity again would go in the denominator. So it makes that first term 0. Negative 10 divided by infinity to any power, 0. Your lower limit, you would have minus a negative 10 over 1. That's where I'm getting plus 10. So this answer is 10. Now the 10 is not really relevant other than it's a finite value. Anytime the integral converges to some finite value, yes, the integral converges, but also the corresponding p-series also converges. Now, this p-series is going to be very helpful for use of the comparison test. What the comparison test is, now keep in mind, a sub n is just the general term of the series that you're working with. So let's say if I can say if a sub n, the general term of some series that we're working with, it's greater than 0, but it's less than or equal to the general term of some other series. Let's say b sub n is a series I can demonstrate the convergence or divergence of. If that's the case, I can say if b sub n converges, then a sub n would also converge. Now that should be obvious because a sub n is going to be less than b sub n. So if I can say the series of b sub n converges, then the series of a sub n would converge because it's smaller than that function. Now on the other hand, well, what if I can show that a sub n diverges? Well, if a sub n diverges and b sub n is greater than a sub n, then that would be evidence that the series b sub n diverges. Okay, now let's see an example of the comparison test here. It says, use the comparison test to determine the convergence of the series n cubed over n to the 5th plus 4n plus 1. Now, instantly, as soon as I do this, and it would be wise if you did the same, go ahead and think about what series you're going to compare this to. I see the degree differential in the numerator and denominator is a difference of 2. So I'm automatically thinking, I'm going to compare this with a p-series of 2. What do I know about a p-series with p equals 2? Anytime p is greater than 1, it converges. So I'm thinking, hey, this series converges. How do I show that? So I need to unequivocally be able to show that this converges rather than just saying, it looks like it's a p-series of p equals 2. Here's how. I use the comparison test. I can say, for all n greater than or equal to 1, the general term of the series I'm trying to find something out about, which is n cubed over n to the 5th plus 4n plus 1, you know that that is less than or equal to n cubed over n to the 5th. Now, think about that for a second. You know it has to be less than. Why? Because I'm making this denominator smaller. So I'm taking those terms out and saying, well, it's that. Anytime you make the denominator of a fraction smaller, it makes the fraction larger. So I know, yeah, of course, this is going to be larger than that because it has a smaller denominator. Smaller denominator, larger fraction. So now I can say, well, okay, then this I can easily reduce down by a factor of n cubed to 1 over n squared. So this is conclusive evidence. Yes, the general term of the series that I'm trying to work with is less than the general term of a p-series with p equals 2. That's what I'm trying to explain right here. The summation of 1 over n squared is a convergent p-series with p is equal to 2, and I always put why I know it converges there. Anytime the value of p is greater than 1, it is convergent. So since this is a convergent series, then I know I can also say, well, since the general term of the series I'm trying to work with is less than or equal to the general term of a convergent series, then the series that I'm trying to work with must also converge, and that is by the comparison test. Now you're thinking, well, that one was pretty straightforward. Does the comparison test get any trickier? Yes, it certainly can. Look at this one with me. I'm asking you to use the comparison test to determine the convergence of the series from n equals 4 to infinity of the square root of n over n minus 3. Now, the very beginning of this, if you look at this, you should be looking at it and saying, well, the degree differential in the numerator and denominator. Numerator's degree 1/2, denominator's degree 1. So automatically you should be thinking p-series with p equal 1/2. What do I know about a p-series with p equals 1/2? It should diverge. Well, how am I going to prove that this diverges. I need to show that the general term of this series is larger than the general term of a divergent series. That's what I try to do here. Now, the values of n in this problem had to go from 4 to infinity, so I said for any value of n greater than 4, the square root of n over n minus 3 has to be greater than or equal to, and now make sure this makes sense to you, it has to be greater than or equal to this. Why? Because my denominator is getting larger. I'm taking away the minus 3. Anytime you're making a denominator larger, it's going to make the fraction smaller. So I know this fraction has to be smaller than this fraction. Now, I could even say this is strictly greater than. It's not wrong to say it's greater than or equal to, but it would I could even say it's strictly greater than. So I'll say this fraction is greater than or equal to, and usually they leave the equality, even though this one's strictly greater than, is greater than or equal to the square root of n over n. Now I know the square root of n over n simplifies down to be what I wanted here. You could reduce down by power, or the 1/2 power, or the square root of n, to get 1 over n to the 1/2. Now, we know that the summation, or the series 1 over n to the 1/2, is a divergent p series. It's with p equals 1/2, which is less than or equal to 1. Anytime the p is less than or equal to 1, diverges. Now, the logic of the comparison test. Since the general term of the series we're trying to work with is greater than or equal to the general term of a series that I know diverges, then this series must also diverge. That is the comparison test. Now, those last two problems I did with the comparison test, that was the comparison in p-series test. The comparison test isn't always done in conjunction with the p-series, though it is normally. Another case, the comparison test, you could do the comparison test in combination with a geometric series. Let me remind you about the geometric series. It's when you have some constant times a common ratio that's going to continually be multiplied in that function after the first term. So the only thing you need to worry about, the constant really becomes irrelevant as far as the convergence or divergence. The only relevance is that common ratio. That common ratio, the absolute value of r, has to be strictly less than 1. So in other words, the terms have to get smaller and smaller and smaller for the series to converge. Okay, now looking at this in some problems here, if I ask you to use the comparison test to show the convergence of the series from 1 to infinity of 2 to the negative n squared. Now this one's, it's a bit tricky because first off you may not even recognize it as a geometric series because of the negative n squared power, although you should recognize it as an exponential because it has a constant base and a variable exponent. So what I'll do, again, we're interested in values of n greater than or equal to 1 and for this problem, and so I can say, well, okay, 2 to the negative n squared. I know that that's the same thing as 1 over 2 to the positive n squared. And now I can say, well, all right, I'm thinking that I could easily say that this is less than or equal to, and again, make sure that this makes sense to you. This denominator has to be larger than this, has to be. Like if I say 2 to the 3 squared, that's 2 to the 9th power, versus 2 to the 3rd, you'd have 1 over 8 here, yet over here you'd have 1 over 2 to the 9th, even way smaller. So I'm making the denominator smaller, which makes the fraction larger. So I can say, well, I know that because this denominator is larger than this denominator, 1 over 2 to the n squared clearly is less than or equal to 1 over 2 to the n. Now, why would I want to get this looking like 1 over 2 to the n? Because I know 1 over 2 to the n I could rewrite as 1/2 to the n power. Why would I want to do that? Because if I have 1/2 to the n as a general term inside of a series, I know that that's a convergent geometric series with r is equal to 1/2. Anytime absolute value of r is less than 1, it converges. Now, does that give us enough evidence? Yes, because I've shown that the general term of the series that we're a part of is less than the general term of a convergent geometric series. So I can say, since 1 over 2 to the n squared is less than or equal to 1 over 2 to the n, then the series of 2 to the negative n squared also converges, again, because its general term is less than the general term of a convergent series. And if you're less than something that has a finite value, you also have a finite value. The last one with this convergence test, and this one's probably even a little trickier, or you could say more beautiful. If I ask you to determine the convergence of the series from n equals 1 to infinity of n factorial over n cubed. Now remember, n factorial means n times every single number less than it. I know that that denominator is just n times n times n. So in order to think of this, and I'm automatically thinking this clearly will diverge. The reason is because that numerator is enormous. It's going to be n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5. Infinitely many values in the product there. And the denominator is just infinity times infinity times infinity. It's wimpy in size compared to the numerator. In order to try to show that, though, here's what I'm doing. I'll say as n approaches infinity, we know that n minus 2 times n minus 1 would be greater than or equal to n. Now that needs to make sense to you. Think about that. Infinity minus 2 times infinity minus 1. Yeah, both numbers are slightly smaller than infinity, but the product of the two would be way larger than infinity. You could think of this as like if n is just a finite number like a million, this would be 999,998 times 999,999. Clearly, the product of those two would be greater than a million. It's even more true as these numbers approach infinity. Now, the reason that that logic right there is important is the way I have to break this apart. This original n factorial over n cubed, I can say is greater than or equal to n factorial is greater than n times n minus 1 times n minus 2 times n minus 3. Because remember, it would keep on going forever and ever and ever. It'd be n minus 4 times n minus 5 times n minus 6. So this numerator here is much less than this numerator. I've went ahead and put all the factors for n cubed in the denominator. Now, I know this larger than this. Now I'll say, well then this is going to be larger than the corresponding term here. Now what I've done is I said, well clearly this n and this n will cancel out. And since n minus 2 times n minus 1 is greater than n, how about if I take that n out of the denominator, but I'm going to make the fraction smaller by counteracting or canceling out two factors of n minus 1 and n minus 2 in the numerator. Of course, it doesn't completely factor out. That's why I'm saying that what I had is greater than what I have left over, the n minus 3 over n. I factored more out of the denominator than I factored more out of the numerator than I have the denominator. This was greater than the factor of n I canceled out, so I know this fraction is greater than this fraction. Yeah. Okay, now in this fraction I could say, well now my numerator and denominator both have a degree of n. I could go in and say, well I think that number should be the n minus 3 in the numerator. It should easily be greater than just a simple 1. And you're like, well of course, because it's infinity minus 3. Clearly that's greater than 1. So the original problem, n factorial over n cubed, I'm saying, well, is by comparison strictly greater than 1 over n. And you say, well, okay, now what are we going to do with that? Well, the series 1 over n is the divergent harmonic series. So then we know n factorial over n cubed is larger than 1 over n. So therefore, the series from n equals 1 to infinity of n factorial over n cubed also diverges, because I was able to show that it was larger than 1 over n, and the series with a summation of 1 over n is divergent, therefore the other series diverges. Now, the last test, which I think you're going to like the best, is called the limit comparison test. You'll see I started off this page saying a better / easier comparison test. Anytime the comparison test can be used, the limit comparison test could be used, and it's more effective. It's easier. There's less ambiguity. Like in that last problem, even though we was able to do it effectively, that's pretty it leads to a lot of ambiguity. I'll say it right. And so students get confused when they see problems like this with a comparison test. Now, if that didn't confuse you, wonderful. But if it did, you might prefer the limit comparison test more so. Limit comparison test, much more straightforward. So, limit comparison test is just saying, if the limit as n approaches infinity, a sub n is going to be the general term of the series you're interested in, b sub n is going to be the general term of a series you know the convergence or divergence of. What the limit comparison test is going to say, if you can take the limit as n approaches infinity of the general term of the series you need to know something about divided by the general term of a series you do know something about, well, what if you can just show it some number L? As long as L is not positive or negative infinity, then whatever the convergence of b sub n is the same as the convergence of a sub n. Now, let me go ahead and talk about this wording here. I say, then the series b sub n converges or diverges if and only if, anytime you see that it looks like a misspelled F, or if, IFF, that means if and only if. So it means the first one happens if the second one happens, and the second one happens if the first one happens. It's a two-way dependence. So the series b sub n converges or diverges if the series a sub n converges or diverges, and vice versa, the series a sub n converges or diverges if the series b sub n converges or diverges. So it's a two-way relationship. It's the if without the second f would just mean this happens if that happens. This is meaning either way here. Now, let's go into our problems to see how that's going to come into effect. So if I look at number 6 here with you, where I'm looking at using the limit comparison test to determine the convergence of the series n equals 2 to infinity of 1 over n squared minus the root of n. Now, before I even worked the problem, if you looked at this and you said, well, the degree of difference in the numerator and denominator is 2. So you'd say, well, let's compare it with a p series p equals 2. The comparison test would fail miserably. And the reason I have, that's why I wrote this in red right here, the general term of this series is not less than the general term of the p series with p equals 2. So you'd say, well, what does it show if you're greater than a convergent series? You haven't shown a thing. In order to show that something converges by the comparison test, our general term would have to be less than the general term of a convergent series. So you'd say comparison test would not help in this instance. However, the limit comparison test is going to be a piece of cake. So notice, I do want to compare it with the p series of p equals 2, the convergent p series, and I'll say, okay, the limit as n approaches infinity of the series we're trying to work with, the general term of that series, 1 over n squared minus the root of n, divide that by the general term of the series I know the convergence of, 1 over n squared. I take this limit as n approaches infinity, I just multiply by n squared in the numerator and denominator, and it gives me n squared over n squared minus the root of n. Then this goes back to Calc 1. You can say, hey, your degree of the numerator and denominator is the same, so inside of a limit going to infinity, you just take the fraction of the leading coefficients. You could also use L'Hopital twice, but that'd be silly. It'd be a lot of senseless work. So you can just say it's the fraction of leading coefficients, it's 1. Now, whenever I say that L value is 1, what that's really showing you is that as n goes to infinity, these two series have the same size. One series is a constant multiple of 1 times the other series. So essentially, they're the exact same size. Well, and I know that this series converges, which means the other series is essentially a constant multiple of 1 times a convergent series, so it also converges. That's what this is saying in more succinct manner. It's saying that the series from n equals 2 to infinity of 1 over n squared is a convergent p series. Converges because p is equal to 2, which is greater than 1. Since the limit as n approaches infinity of a sub n over b sub n is 1, by the limit comparison test, we can conclude that the series of our problem also converges. Now, let's look at a more difficult one, and this one would be a geometric series. And anytime you see exponential functions in there, you know it's a geometric series. So in this one, I have the summation from n equals 1 to infinity of 5 times the function e to the n plus n divided by the exponential function e to the 2n minus n squared. Now, one thing you could go ahead and do in this problem, exponential functions rise so much more quickly than any polynomial functions in existence. The polynomial functions in this problem become completely irrelevant. You could just ignore them. Exponential functions, as n goes to infinity, rise exponentially more quickly than any polynomial. Even if I had something like e to the n divided by n to the 1000th power, as n goes to infinity, that answer is infinity, because any exponential will grow infinitely times larger than any polynomial. But now, I went ahead and broke this down algebraically to think about it. And I said, well, okay, the numerator 5 times e to the n plus n, my denominator e to the 2n minus n squared. What I went ahead and did is recognize that this is a difference of two squares. E to the 2n is e to the n times e to the n. Obviously, n squared is n times n. So I wrote this denominator as e to the n minus n times e to the n plus n. That e to the n plus n canceled with the factor of e to the n plus n in the numerator, leaving me 5 over e to the n minus n. Now, I went ahead and I just compared. I could have left the 5 in the numerator, but all I was thinking of is that this is a constant over an exponential function, and I needed to write this as some easy geometric series. Well, I knew if I wrote it as 1 over e to the n, then this is the geometric series 1 over e to the n power. And what do I know about 1 over e to the n power? Well, r is equal to 1 over e, which is less than 1, so that's going to be a convergent geometric series. So then, if I know that this is a convergent geometric series, if I can show that the limit of the function I'm trying to work with, or the general term of the function I'm trying to work with, divided by this is some constant multiple, then it's evidence that it also converges. That's what I tried to do down here. L is equal to the limit as n approaches infinity, the general term of R series, divided by the general term of the geometric series that I know converges. So now I can go in and say, well, this is the limit as n approaches infinity. All I've done is I multiplied by e to the n up here, gave me 5 times e to the n times e to the n plus n, all over e to the 2n minus n squared. Then I could say, well, I could have simplified just like I did up here, but in the end, I just wanted to go ahead and multiply out and say this e to the n times e to the n, I'll get e to the 2n. Of course, the 5 would also distribute to this term. Once I'm at that point in the problem, I know in terms of exponential functions, the only thing that's relevant is the highest powered exponential functions in the problem. Everything else is going to be infinitely times smaller than that. So as soon as I was inside the limit as n approaches infinity, I just ignored these terms right there because they're going to be infinitely times less than the other terms. So then I said, well, what's the limit as n approaches infinity of 5 times e to the 2 times infinity over e to the 2 times infinity? Clearly the exponential functions would cancel and leave you with a constant of 5. Now, because that constant is 5, and I can say, well, then that's showing me that my function is merely as n goes to infinity, it's essentially a multiple of 5 times a convergent series. So I say, since 1 over e to the n is a convergent geometric series, with the absolute value of r equaling 1 over e, which is less than 1, since L is equal to 5, by the limit comparison test, we can conclude that our series also converges. Now guys, I know that this stuff, it can be really strange to begin with. A lot of people struggle with all these convergence tests. Once you get used to them, they're going to start to make a lot more sense. But it seems like a very foreign concept at first. Please don't get frustrated with it and let me know how I can help you out.